So what we need, therefore, is to design a circuit or come up with circuits where you have two inputs, VA and VB, correct? And you want to figure out which is greater. Okay. So, any suggestions? What can we do at a conceptual level? Basically, what we want is a logical signal, which is logic high if VA is greater than VB, and logic low if VA is smaller than VB. Correct? So, what do you think we can do? I mean, see, to do something, there are many ways of doing it, right? Your way or my way will not be the only way of doing it. Correct? First thing we need to do is we definitely need to at some point subtract VA from VB and figure out if that difference is greater than 0 or less than 0. Okay. So then we might say, you can start off with a simpler problem. We say, let's try and figure out if VA is greater than 0 or less than 0, right? If VA is greater than, so this is equivalent to saying once we figure this out, it follows that we can figure out if VA minus VB is greater than 0 or VA minus VB is less than 0, which is equivalent to saying we can figure out if VA is greater than VB or vice versa. Correct? So I have transform the original problem into something which seems slightly simpler. Okay. What all can you do? Let's assume that we have supplies which are dual supplies for the time being. I don't think there's any fundamental difference, but it makes reasoning easier. So you have plus VDD, then you have minus VDD, right? And the input is VA, correct? And you want to compare it with 0 and produce a logical one which is plus VDD if VA is greater than 0, and you want to produce minus VDD if VA is smaller than 0. What do you think I can do? Conceptually, let's not get into transistor level details yet. Pardon? Oh, yeah, that is what we're trying to do. But can you suggest what we can? How do we go about this? So the one thing that comes immediately to our mind is you amplify this. This will give you some A times, let me call this not A but K. This will give you K times VA, correct? And and you want this to reach something close to VDD or something close to ground, minus VDD. So in other words, if this has to be approximately VDD, the K required will be how much? If the input is VA and you want the output to reach VDD, you need a K of VDD by VA. Correct? Any input smaller than VDD by, K min is VDD by VA. In other words, any voltage at VA which is smaller than VDD by K, what happens? If the input is if VA is positive, but VA is basically say VDD by 2K, what happens? What is the output? VDD by 2. So is that a logical level or no? It's not yet reached logic high. Okay. So in other words, if you put an amplifier with a gain K, then your resolution, right? I mean, how accurately you want to resolve the input, okay, or the band of uncertainty is what? This is 0. You will not be able to make out if VA is greater than 0 or less than 0 if VA lies in this band which is on top VDD by K and in the bottom minus VDD by K. In other words, you need a voltage of at least VDD by K for the output to reach a logical level. Does it make sense? Okay. So, I mean, obviously you want to make this band of uncertainty small or large? Yes, people, you want this band of uncertainty to be very small or very large? You obviously want to make it very small. So, if K is not large enough, what will you do? If the band is too large, it means that K is too small. So you have to increase K, right? So how do you increase K? What is the most obvious idea of increasing the gain? That's not obvious. Is that obvious? What is the most obvious thing you can think of? You cascade another stage, right? You copy and paste. Right? And what will happen to the band of uncertainty now? It will reduce to plus minus VDD by K square. Right? So, and if that is not good enough, what do? Put another gain K cube and so on. Right? So you see that the uncertainty with which, or this band of uncertainty around this threshold value which is 0, okay, is inversely proportional to the gain of the amplifier, right? And I mean, clearly any physical amplifier which is operating with rails VDD and minus VDD, the output can never be larger than VDD or smaller than minus VDD. So we don't have to worry about what happens when the input is, say, if the input here happens to be very large. No, okay, does this mean that it will be K cube times whatever input it is? It will be K cube times whatever input it is only for a small range. If the output happens to be larger than VDD, it will get limited to VDD or to minus VDD as the case may be. Is that clear? Okay. But if the input is very large, we don't have to worry. Our problem only comes when the input is very small or is very close to the threshold. Right? The problem we have in resolution is only when the input is very close to the threshold. You understand? So, for example, to give an analogy, if somebody goes to an interview, correct? It's very easy to figure out if the fellow knows everything, if the fellow knows, is very good or very bad. That's very easy to figure out. But only problem is when you have borderline cases. Correct? Then only you have to be very careful. Right? When people are very good, it is very obvious. When people are very bad also, it's very obvious. So just like that, if the input is way above the threshold or way below the threshold, no problem at all. The only problem is when people the input is hovering very close to the threshold. That's when you have to do a careful job. Is that clear? Okay. So, obviously, in order to minimize this band of uncertainty to 0, is it possible at all? In principle? What can we do? And lunch is very good, so everybody is. Yes, come on, people. K has to tend to infinity. If the width of the uncertainty band has to reduce to 0, K has to become infinite, which means that how many should I cascade? I have to cascade infinite number of these amplifiers to get the infinite gain required. So clearly that's not very practical. Does that make sense? Okay? Okay. Alright. So let's see if there are any other ways of doing this. Okay? And typically it is always that you are given an input, right? And in analog form, if the input exists somewhere, what does it mean? In other words, if you want to store something in analog, what will you do? If you have a voltage and you want to store it and come back later and then see what the voltage was, you charge it you hold it as a charge on a capacitor. So let's assume that you have an input, right, which is held on a capacitor, a VA. Okay. Now we want to figure out if VA is greater than 0 or smaller than 0. And one way of doing this is the following, right? If VA is greater than 0, right, I will push current into this node. Okay? If VA is smaller than 0, I will remove current from this node. Correct? If I push current into this node, what happens to the potential of this node? It will go on increasing. Eventually what will happen? So push current into a node when VA is greater than 0. What will happen? The voltage will keep increasing, correct? Because you're pushing current into the node. In other words, there's more charge on the capacitor, the voltage keeps increasing. Eventually what will happen? Ideally it will go to infinity, but in practice it will saturate at the supply, at VG. Correct? Okay? And in other words, you want, similarly, if VA is smaller than 0, you will pull current from this node. So what will happen to the voltage? It will go on dropping. Ideally it will attempt to go to minus infinity, but in practice it will get clipped off at minus VDD. We assume dual supplies, right? So plus VDD or minus VDD. Correct? Does it make sense? In other words, depending on the current, on the value of the voltage VA minus 0, we are pushing a current which is dependent on VA. Correct? So in other words, onto this node, what we are doing is pushing the current which is dependent on VA minus 0. Correct? If VA is greater than 0, what should be the value of this current? It should be proportional to the current, the input of this current. The voltage controlling this current is VA, correct? And the output is the current. So the ratio, the quantity that relates the current to the output must have dimensions of transconductors. Does that make sense? So this is Gm times Va minus 0. Is that clear? So one thing you can see is that if Va is greater than 0, current will flow into the capacitor, causing Va to go up, which will cause more current to flow, which will cause the voltage to go up even more, which will cause even more current to flow, and eventually what will happen? If Va was initially greater than 0, then eventually what will happen to this, the voltage on the capacitor? It will hit the positive rate. Is that clear? On the other hand, if Va was initially greater than 0, it will eventually hit Vd. Does it make sense? Okay. On the other hand, if Va was initially less than 0, it will eventually hit minus Vd. Does it make sense? Correct? So let's look at the rate at which, how long it takes to hit VDD. Right? We know definitely for sure that it will hit VDD. Obviously it takes time. We want to find out how long it takes. Correct? So if the initial voltage was Va, the current flowing into the capacitor is Gm times Va. Correct? So Gm Va is nothing but C dV by, let me call this Vc, and at t equal to 0, Vc is Va. Right? So Gm times Vc is C dVc by dt. The current flowing into the capacitor, right, causes the voltage to go up. And if Vc is the voltage across the capacitor, C dV dt is the current flowing through the capacitor, and that must be equal to Gm times Vc. Does it make sense? Alright, which means that Vc is C by Gm dVc by dt. What kind of equation is this? This is a linear differential equation of first order. What is the solution to this equation? Pardon? It's Vc of 0 times, please check carefully, e to the minus or plus? Okay, let's understand what happens physically. Okay, so if Vc is initially positive, what happens to the voltage? Let's say Vc was initially positive, correct? What is the current flowing into the capacitor? It is Gm times Va. So what happens to the voltage? It must increase, correct? It starts doing this. Then what happens? Please note that this is the voltage across the capacitor, and this is also what is driving the current source. So now the voltage across the capacitor is increased, which means that the current source is pumping has also increased. So what do you think will happen to the current is increased, so what happens to the slope of the voltage across the capacitor? It must, the slope of the voltage across the capacitor is proportional to the current flowing through it. Correct? More current, quicker rise. Initially, there was some voltage, right? And that causes the voltage of the capacitor to increase. Now, the voltage across the capacitor is large, which is also what is controlling the current source. So, what will happen to the slope will increase, right? And then it will keep going this way until the voltage hits VDD by plus VDD. Correct? So, does this look like a rising exponential or a decaying exponential? Rising exponential. So, what should be the output voltage? Vc of 0 times e to the plus t by tau, where tau is c by g. Does it make sense? Okay. So, and what is Vc of 0? When we started off, Vc was Va. So, Vc of t is nothing but Va e to the plus t by tau. Correct? And so, how long does this take to reach VDD? Yeah, you want to make this equal to VDD, correct? Which means that the t is nothing but tau ln of VDD by Va. Correct? This makes sense. Why does it make sense? Oh, but what is this telling you? If Va is small, come on people. If Va is small, it takes a long time. Correct? And Va is large, it takes a short time. But at any rate, in both cases, if you wait for sufficiently long enough, then the output will always reach VDD. Is that clear? Alright? So, compared to simply putting amplifiers in cascade and getting a large gain, where you in principle need to put infinite amount of time, infinite number of amplifiers in cascade, this seems like a more hardware efficient technique, where, pardon? Correct. So, all that we have done is we have reduced the complexity of, instead of repeating so many amplifiers, now we have only, all that we need is one voltage controlled current source. The GM is nothing but a voltage controlled current source. It's only one voltage controlled current source, right? And now given time, okay? It now takes time. If you wait long enough, you'll be able to resolve. That band of uncertainty becomes smaller and smaller and smaller. Does this make sense? Okay? So you can see this is a lot more hardware efficient way of doing it. His point is valid. If Va is 0, then you will never be able to decide. You understand? Okay? Alright? And in the other case also, even if you put million amplifiers in cascade, if Va is 0, you will never be able to decide again. Correct? You understand? And one more thing, practical issue with the amplifiers is that no amplifier is instantaneous. It will give you k times Va only after some time. Which means that even though you put many amplifiers in cascade, right, and you expect k to the power n times Va, that will also happen after some time. It will not happen instantaneously because the signal has to pass to the first amplifier and the second amplifier and so on. Right? So, it's not as if this is, this doesn't seem to be that bad after all. Especially given that you are using only one voltage controlled current source. Does this make sense? Okay? And this is like again to give you the interview analogy, right? if some fellow goes into the interview room, if he's very good or very bad, he'll come out very quickly. You understand? The fellow who takes longest means that the committee has to really question him hard and really figure out if this guy is pass or fail. You understand? Right? Same thing here also. Right? Only if the input is hovering very close to the threshold, it will take up. If the input is hovering close to the threshold, in other words, VA is very close to 0, then it will take a long time. Right? If VA is very high or very low, then the output is reach VDD very quick. Does it make sense? Okay. Now the question, so in other words, the resolution depends on time. Correct? So if you want to reduce the uncertain band to a small value, you must wait for longer. Does that make sense? Okay. So this, we seem to have a reasonable way of, by using a little amount of hardware, to be able to resolve whether VA is greater than 0 or smaller than 0. But that's not what we intended to solve in the first place. Right? 0 is not what we want. We want to figure out if VA is greater than VB or you have two inputs VA and VB. You want to figure out if VA is larger or VB is larger. Equivalent. Correct? So this is straightforward. So you have two inputs. Let's say they are held on two capacitors. One is charged to VA. One is charged to VB. If VA is greater than VB, now you should tell me. Right? Now what should I do? Let's reuse the same idea that we used earlier. When VB was 0, what current was we pushing into the capacitor? GM times VA minus 0. Now that it's not 0, it is VB. So what current must I push in? So I must push in a current here which is GM times VA minus VB. Correct? And here what must I push in? GM times VB minus VA, which can be written as minus of VA minus. Correct? So now what happens if VA is greater than VB, right? So this is node, let me call this A and then V. So if initially the voltage across the capacitor on the left is larger than the capacitance, the voltage across the capacitor on the right, once I start off the system, what will happen? When originally, let's say this was VA and this was VB, what will happen? Yes, madam? VA will, since VA is greater than VB, current is pushed into the capacitor on the left and pulled out of the capacitor on the right. So the voltage on the capacitor, on the left side capacitor will, left side, it will keep increasing. Okay. And what will happen to the voltage across the capacitor on the right? It will keep decreasing. Eventually what will happen? VA will go to VDD, VB will go to minus VD. Right? So it's like the rich keep getting richer and the poor keep getting poorer. Right? Eventually, the rich guy will have all the money and the poor guy will have nothing left. You understand? And again, this also is exponentially increasing, because if VA minus VB was very small to begin with and positive, current will be pushed into A and sucked out of B. So the difference is increasing, which means that the current will increase, which means that the difference will increase even faster, which means that the current will increase even more, and correct? You understand? So in other words, like what we did last time, if we plotted VA minus VB as a function of time, if VA minus VB was positive, what will happen to VA minus VB as a function of time? It will increase exponentially until VA becomes plus VDD and VB becomes minus VDD. So eventually the difference will saturate to 2 VDD. Correct? On the same, by the same token, if VA minus VB is negative, what will happen? It will also exponentially increase, but exponentially the magnitude will increase, but it will go towards minus VD. Is that clear? Okay. So this seems to be what we want to do, right? Because we want to compare Vin with Vref. All right. You understand? Okay. So how can we do this? So in other words, what we want to do is this is a symbol for a transconductor, correct? And this current is GM times VA minus VB. Alright. We also need a transconductor which is Does it make sense? Okay. Alright. So, this is the basic idea. If you already have VA and VB, one way of figuring out for sure if VA is greater or VB is greater is to do this. Where the difference between VA and VB will exponentially increase, and that exponential increase is governed by the time constant C by GM. And why does this C by GM make sense? If GM increases, it means that you are pumping more current, which means that the voltage across the capacitors will rise up faster. Similarly, for the same current, if you reduce the capacitance size, the capacitors will charge up much quicker. Correct? So you can increase the speed of this whole process by either decreasing C or increasing GM or do both. You understand? Is that clear? Okay. So a couple of practical issues. One, of course, is that please note that we don't want to figure out if VA is greater than VB. Okay. Whatever. Get them to VDD or minus VDD and then go to sleep. You understand? What should we do? After you made the decision, if we all go to sleep, what will happen? What else? The next input has to be digitized also, isn't it? So what should happen? You must have some way of, this is not just good enough. We should have some way of being able to store the inputs onto VA and VB after you do this. Once you finish figuring out VA and which of them is greater, you need to get ready for the next cycle. Correct? In other words, you want to be able to write or charge these capacitors to some input voltage, right? So what do you think I can do? If I want to charge the capacitor to a voltage, what should I do? I should have the input and then you put a switch, and similarly, so VA, let me call the input V in 1 and V in 2. Let me call this phase of the clock which controls the switch phi 1. Okay. Alright. So when phi 1 is high, the switches are closed and the capacitors are shorted to V in 1 and V in 2. Correct? So the voltages, when phi 1 is high, the voltages across the capacitors are simply V in 1 of t, which is a continuous thing, perhaps, and V in 2 of t. Correct? When phi 1 is low, in other words, when the switches are open, then what happens? Then these two, current sources take over, and basically this any difference gets amplified more and more and more and goes to either VDD or ground. So when phi 1 is closed, right, when the switches are closed, do you actually need the regeneration? Do you need this amplification process when the switch is closed? I mean, okay, by the way, what is this guy here doing? Yes, so the aim of that stuff drawn in the red box is to figure out which of them is greater after they've been sampled. Correct? So when phi 1 is high, the sampling phase is going on. Correct? During that time, you do not need this mechanism to be turned on. Does that make sense at all? Correct? You understand? Okay? Now you can think of the phi 1 as return test phase and phi 2 as, and phi 1 bar as the interview phase. Correct? You do not want the interview panel to be, talking to all candidates, right? You want them only to talk to candidates who passed the written test, right? So during phi 1 is basically what, you can think of it as the time when the input could be changing, V1 and V2 could be changing, but when phi 1 goes low, right? When the switch is open, those two, the inputs V in 1 and V in 2 at those instants are the ones that you wish to compare. Correct? So when phi 1 is high, these transconductors need not. Do you need them or don't you need them? You don't need them. So you must have it's not just enough to have some voltage controlled current sources. You must have some mechanism of turning them off. Correct? So let me therefore have two phases for the time being, right? So one is called phi 1, the other one is called phi 2. So phi 1 is the phase where the input is sampled, and when phi 1 is high, you do not want the GMs to be working. You want them to work only when phi 2 is high. You understand? So in other words, these current sources, voltage controlled current sources, are controlled by this symbol. I mean that these things act like voltage controlled current sources only during this phase phi 2. Okay? Is that clear? All right. Yes, okay. So, during phi 1, what is happening? Inputs are sampled on the capacitor. Correct? During this phase, we do not want the current sources to operate. Right? You want them to operate only during, after you sample the inputs and the inputs are safely held on those capacitors, that's when you want these two current sources to do their thing. Right? In other words, they should be activated only during, for some time, only after phi 1 has gone low. Is that clear? Yeah. I'll come to that. Okay. So, once phi 2 is over, what do you think will happen to this voltage and this voltage? Depending on what values were held on those capacitors just before phi 2 began, right? Pardon? The larger one will go to VDD, the smaller one will go to minus VDD. Does that make sense? Okay. So, at the end of phi 2, this node is sitting at plus or minus VDD. Similarly, this node is also sitting at plus or minus VDD. Okay, depending on the signs of the input. Correct? Now, the question is this, then what happens, then what do you think we can do? I mean, so now you're done with your process. Correct? You figured out which one of them is? Come on people, some more enthusiasm. Is it going too fast? Okay, alright. So, one of them is VDD, one of them is minus VDD, so you're done with this job. What is the next job? First of all is make sure that somebody knows what you know. Correct? So, there must be some flip-flop or something. Now it's a logic value. It's either plus 1 or, logical 1 or logical 0. So that has to be stored on it doesn't help if you know and then you forget and then start doing the next job, isn't it? So somebody must know that you've done the job. So that you can do by sampling the logical output on a flip-flop. Okay? And so that is straightforward. Right? So what should I do for the next cycle? Okay. One thing one could argue is that if the input voltages are ideal voltage sources, right, if V in 1 and V in 2 are ideal and these switches here have zero resistance, then, once phi 2 goes off, these guys are dead. Correct? And all that has happened is that this is over, this is shorted, this switch also is shorted, and V in 1 appears directly across the capacitor, V in 2 appears across the second capacitor. So in principle, there should be no problem at all, because you have an ideal voltage source charging a capacitor. Correct? But obviously, whoever is driving this comparator has got any practical voltage source will have a finite output resistance. Correct? So in other words, if I just simply try to do, in principle, this is what it is. But in practice, what happens? There is some resistance in series with C. So what happens? And this voltage, this capacitor is initially charged to either plus VDD or minus VDD. So what do you think will happen to the voltage across the capacitor? Please note that we only have a time interval phi 1 during which this is connected. Correct? So what do you think will happen to the voltage across the capacitor? See, there are two things now. This is nothing but the analysis of a first order RC circuit, correct? With some initial condition. So we can do it with superposition, right? So let's say this originally voltage was VDD, correct? And how can you do this? So can somebody tell me how you will be able to solve the voltage across the capacitor as a function of time? Correct. This is equivalent to a capacitor with an initial voltage can be treated as a capacitor without an initial condition plus a voltage source which turns on with a voltage step at t equal to 0. So this is VDD. Correct? You understand? So you can do this by superposition, right? So assume this VDD was not there. And if simply there was Vin, what will be the voltage across the capacitor as a function of time? Vin, if there was Vin, which is also a step, then it will eventually reach Vn. Okay. Alright. On the other hand, if there was VDD, what will happen? It will discharge to ground with this time constant. Correct? In other words, trying to charge this initially charged capacitor to Vn, okay, depends on the RC time constant. The capacitor will forget its old voltage with the time constant of RC, and similarly it will learn its new voltage also with the same time constant. Correct? So what do you think will be the voltage at the end of this time? Let me call this width T1. It is nothing but Vin into 1 minus e to the minus T1 by RC plus VDD e to the minus T1 by RC. Correct? So you can see that the voltage across the capacitor, okay, it remembers the past and loses that memory with time, where the unit of memory is basically RC. Similarly, it's able to track the input voltage also with a time constant of RC. You understand? Now do you want this circuit, do you want a circuit which remembers for a very long time or which forgets very quickly? If in other words, if T1 is very short, I mean, do you think this RC time constant should be a large number or a small number? Ideally it should be 0, because you don't care about the last sample, that's all, that's done. You need to quickly charge C to the new input. But whereas this is telling you that if RC is large, what is happening is that there is a lot of inertia charging to the new input as well as forgetting about the old input. Does that make sense? So if it doesn't forget the old input adequately, what do you think will happen? Let's say RC is not low enough. What do you think will happen? Yes? No. You have made an error because you are ideally interested in sampling Vn. Correct? But what you have actually done is you only have now a fraction of Vn. Correct? Because this has not reached the full Vn yet. Okay? That might be not too bad, but there is a worse thing happening, and that is it is not yet forgotten VDD. What was there? The last one. You understand? Correct? I mean, this is pretty much like election, right? So, you do not want any bad things to happen to your party and your party members. You make sure that all your candidates behave properly for a short window before the election, right? If they have done it 5 years back, nobody knows. Public memory is very short. You understand? So whatever good they do, same thing happens to good things also, right? Nobody remembers who built this nice road, right? Okay, if you did it 5 years back. But if you did it 5 days before the election, then clearly people remember, right? So similarly, so any good deed that you have done long back can get erased by a bad deed you do today. Similarly, and vice versa, correct? So that is pretty much what it is, right? So the input being, what do you call it? The memory is very long. Then you remember the past, which is certainly something that you do not want, right? Both here and as a political party, right? Okay. Clearly, if t becomes infinite, what happens? So, if t becomes infinite, it basically means that r is infinity, one way of achieving that, which basically means that whatever VDD was there, it will remain as it is the next time also, because it has not lost any charge at all. Does it make sense? Okay. So, clearly one way of, so what you have to do therefore is to reduce this time constant RC as much as possible. Yes, sir.
is always much lesser than VDD.
Yes.
Right? So why not make that VDD contribution to 0? So you can just
that's the correct. So he's overtaken me here, right? So you can see that the only way to make this work is to make RC 0. That is obviously not possible, right? You can't make R equal to 0. So we have to be able to figure out some way of making these two capacitors forget their past, correct? In spite of the fact that one of them is VDD and one of them is VDD and one of them is minus VDD. We need to be able to make them forget their past so that even though you have finite RC. Does that make sense? We need to forget the past. That the way we have it now is impossible because it's not possible to get 0 R. Correct? Right? So can we figure out some way of making these two capacitors just lose that VDD and minus VDD? One of the capacitors is at VDD, one of them is at minus VDD. We need to be able to figure out a way of making them lose their memory, what they have done in their previous life. Right? How would we do that? Yes? So, very good. Right? So, one idea is to, after phi 2, you have a third phase where you, for a short time, you take you short both the capacitors to ground. So they have lost all prior memory. In other words, this is phi 3. An alternate way of doing it, anybody else can hazard a guess?
Can you just make that GM adjust so that current voltage is 0?
No.
Current to the upper one, if I want to plot the left-hand side capacitor.
Yes.
And if you do is V plus minus plus minus 2 voltages, I just repeat that its difference is 0.
Yes. Yeah. So what he is suggesting is instead of connecting each one to ground, you can alternately just simply zap the two together. Correct? And what happens now? The voltage of one was plus VDD, the other one is minus VDD. You short the two together, you get 0. Correct? You understand? If you do not do this, what will happen? What will happen? Yes, what will happen is that the voltage stored on these capacitors will get corrupted because of because of the decision made in the last cycle. Correct? Okay? Alright, and this is what is called hysteresis. I hope this is the right spelling. Pardon? Is it okay? Or SYS, is it? It's appropriate that I forget because we do not want to remember anything in the past. You understand? Okay? So, okay. And this will be especially critical for inputs which are close to zero, which are close to zero or far away from zero. When will you, okay, let's say RC is small but not very small, right? So, what inputs are likely to get affected? Please note that we are only trying to figure out if input is greater than 0 or smaller than 0, right? Or in this case, VA is greater than VB or smaller than VB. So, to that extent, we can actually tolerate some error because we are not really interested in finding what the exact value is. We are only interested in figuring out if the input is greater than 0 or less than 0. Here you see that the difference, this of course is reduced in magnitude because of memory, because the capacitors are not charged to the full V in, right? And there's also, they have not forgotten the old decision. So, the inputs that are most likely to get affected are those things where the input is near to 0. Correct? If this part is small, then it's very easy to get corrupted by this large VD. In fact, the biggest problem will be when the input has the biggest problem for this will happen, as you will understand, when the input in the previous cycle was just above, let's say it was above 0, right? And in the next cycle has gone to just below 0. Okay, then what happens? The input in the first comparison was just above 0, so the decision made would be on the two capacitors, the voltages would be like this, and then these things have not decayed fast enough, right? And you are attempting to charge this to a small difference in the opposite direction, right? So what will happen is that the VDD, which is not yet decayed, will simply overwhelm the small negative input, right? So the best test for hysteresis, to make sure that your comparator doesn't remember the past, is what? You connect it to an input which was, positive in one cycle and slightly negative in the next. If your comparator has no hysteresis, then the output should be, +1 in the first cycle and -1 in the next cycle. If there is hysteresis, you will see that it is +1 and +1, because it's not really a fault of the mechanism. It's just that the inputs itself have been corrupted, right? And the poor fellow is just looking at wrong inputs and making a decision on. You can blame the two voltage controlled current sources, for this mess up. Is that clear? Okay. So right? So this is the basic idea behind a comparator, right? And please note that what I want to point out and is very important is that this has got no transistors in it. Okay, we have to finally realize all these. What all do we have to realize? The switches and the voltage controlled current sources, which are also called transconductors, using transistors. But this is the basic idea. Okay, and those of you who have not dealt with transistors before or not very comfortable should still be able to understand this part, right? Because there is no assumptions made, okay, on prior knowledge at all. This is pretty much it comes from first principles, in other words. Okay? And as a general rule, whenever you see a new circuit, you must always, rather than get into the transistor level details first, it always makes sense to look at what the basic idea is. Right? Okay? And then you can always replace stuff with transistors. But, and it's all, I mean, in general, you'll always understand things much better if you know why you're doing what you're doing, rather than copy paste, some circuit you saw somewhere. Alright? So, given that this is the idea, and we know precisely what each one of these clocks is doing, correct? And why we need every one of those components there. One thing, of course, is that we'd like to be able to, so basically the time taken to make a decision, therefore, is proportional to how long does it take to complete one full operation. What all do we need? We need to do three things. One, sample the input. Two, charging the capacitor. I mean, sampling the input is that's where you're charging the capacitors. Then phase two, where we are converting that small difference into a very large difference, correct? Using the current, whatever, right? And then the third phase where you are zapping the two capacitors together. Okay, so the time it takes to complete the whole operation is obviously the sum of the times taken to complete each operation. The time it takes to complete the first operation, which is charging the input capacitors, right, depends on what do you think? It depends on the resistance of the switches, also depends on the output impedances of the voltage sources driving the comparator, right? Correct? Times C, which is these capacitors. So to reduce the time constant as much as possible, what will you do? Of course, you reduce the switch resistance and the output impedance to the extent possible. But can we do anything here? You use a smaller capacitance, right? So what is the smallest amount of capacitance you can use here? How small can C be? No. In principle, what is the smallest C you can use? You want C to be small, so I will make C smaller. Then you want it to be small, I will make it even smaller, right? And go on doing this. How far can I go? I just remove these all together, right? Because I can rest assured that any real switch and any voltage controlled current source, etc., will have their own parasitic capacitance. So I don't need to explicitly put in any capacitance there, right? So when I say the RC time constant, I'm talking about all the parasitic capacitances that will come in at those nodes because of all these components connected there, right? Okay? So I don't need to make things any worse by deliberately putting capacitance. Is that clear? Okay? So right now the schematic assumes that there is some parasitic at A and B. So does it make sense? Okay. Now these switches, what all do you think I can do with the switches? I mean, how do I implement the switches? You can use pass transistors here, right? So I'm not going to draw them because the circuit schematic will become messy. But basically, use pass gates. Now the only thing that remains is, so we have taken care of this guy, these guys, this guy. So the only thing, and this guy. So the only thing that remains is the transconductors, And this is not just any old transconductor. This needs to, you need to be able to turn it off. Correct? Okay, so let's try and see if we can use anything that we have learned, any prior knowledge. Okay, let me not give away the answer. So what we are trying to do is generate, so if this is whatever, V in VA and VB, we are trying to generate a current which is GM times some GM times VA minus VB. So now, for those of you who have exposure to transistor level design, can you think of a simple circuit which will take the difference between two voltages and convert it into a current? Okay, so one idea is that why don't you use a transistor, apply VA here and then VB here. What are the problems with this? Pardon? One problem is that, as he pointed out, VA minus VB, when it becomes negative, obviously the transistor is off, right? Okay. Another thing, as he points out, is that the impedance looking in at VA is very high. There is no DC current, but VB is the source of a transistor, right? Okay. So clearly, this is not a workable idea. Anything else? Please follow my question again. You want a current which is proportional to the difference between two voltages. What circuit, simple circuit, basic building block is capable of operating on the difference between two voltages? The differential pair, right? So let me just quickly review that. You have a tail current. If this is VA and this is VB, what is this current? If this is, let's say this is 2I. No. If VA minus VB is a small voltage, what do you think? If VA equal to VB, what is the, I'm assuming that the drains are connected to a high potential so that the transistors are operating in saturation. So if VA equal to VB, what is the current on the left? If VA equal to VB, so let's say both of these are connected together, what are these currents? This is I and this is I, correct? Now if VA minus VB is a small number, what is the current now on the left side? The currents in the left will be more than the current on the right, okay? By how much more? Yeah, so it will be, the current on the left will be I plus some GM, right? If the transconductance of this transistor is represented by 2GM, then this will be GM times VA minus VB. Okay? And I am calling the transconductance of the transistor 2GM just so that I don't get that 1/2. Okay. Similarly, this current, what will be the current on the right leg? It will be I minus GM times VA minus V. Correct? Okay. Alright? And it's not necessary to have a current source. You can also have a resistor. Correct? Does that make sense? And what do you think? Can you suggest a simple way of turning? We need not only just a voltage controlled current source, but we also need to be able to turn it off during some time. Correct? So what do you think I can do? Pardon? You put a switch. Okay, if I do this whole thing is dead. Correct? So to make this depend on some phi 2, what I need to do is have a resistance which is there for some time and not there for some time. So you need a resistance which varies depending on control, and that is simply a MOS transistor operating like a switch. Correct? Okay. You understand? I mean, also another thing is that there is nothing holy with an NMOS differential pair. This is all an NMOS differential pair, isn't it? I can do the same thing with a PMOS. For example, okay, and what should the top switch be connected? Pardon? Phi 2 bar. Correct? So this, for example, correct? If you know, if I can use an NMOS differential pair and a PMOS differential pair, I can put the two together and connect them in parallel, that will still work. Okay. Now if I short these two, just conceptually, pardon? Yeah. So what is the, so if I plot, if I let me connect this to minus VDD, sorry, and if this is VA, this is VB, and if I short this to ground, what is the current that flows? Can you tell me? I mean, please note that this current, apart from the quiescent value, is proportional to GM times VA minus VB. What about this current? It is also proportional to GM times VA minus VB. So this is equivalent to what is happening when I put the two together. It is GM of the NMOS times VA minus VB plus GM of the PMOS times VA minus VB. Does that make sense? Similarly, this current is in the opposite direction. Correct? So you can think of this as giving you both the currents that you are looking for, right? The Norton equivalent looking here is this is proportional to this current going in is proportional to VA minus VB. Correct? Yes? No? Yes? What about the current flowing here? Minus of VA minus VB. This is, it's proportional to this. Correct? Alright, so now we come pretty much to the end of the journey, right? So what are we supposed to do? Which must go where? So this, you now have a block which is giving you not only VA minus VB, correct? I mean, let me, since our basic diagram drew stuff like this coming out, this is proportional to minus VA minus VB. This is proportional to VA minus VB in this direction. Is that clear? Okay. So what are we supposed to do? Recall we had these two capacitors, plus VA minus VB. The guy pushing the current, which is VA minus VB, must come into, look here. You have two currents, VA minus VB and minus VA minus VB. The one which is proportional to VA minus VB must connect to VA. So what should I do here? So I need to, therefore, connect this fellow to VA, correct? And this fellow to, correct? And we need to add all the extras. Which are, what all do we need to add? We need to add the switches phi 1, correct? And we need to add also one more thing. Phi 3, which needs to short VA and is that clear? Okay, and basically at the end of phi 2, what will happen to these two voltages? And this is the VA, this is the VB. At the end of phi 2, the two current sources would have done their things, and one of them, either VA or VB, will be at VDD, other one will be at minus VDD. Okay. Of course, one thing now left over is to, we know that we operate mostly with single supplies, right? So if you have positive supply and negative supply, and if you want to make the circuit operate with single supply, it's very easy. Just add VDD to every node voltage, correct? So in other words, this will become 0, and this will become 2 VDD. But you can always call 2 VDD, call it as VDD, right? So this becomes the, you understand? Alright. So this is the, so this is an example of a comparator, right? A very, very basic one, where all that it's doing is taking V in 1, V in 2 and so phi 1 is called the sampling phase. Phi 2 is the phase where the rich becomes richer and the poor becomes poorer, right? So this is called the regenerative phase. And phi 3 is where past memory is cancelled, or rather zapped. That is called the reset phase. And the regenerative time constant is basically Gm by C parasitic. Please note that the total capacitance is basically the sum of all the capacitances at this node, right? That includes this gate capacitance, switch capacitance of the parasitic capacitance of the switch, and so on, right? So the time constant is, therefore the regeneration time constant is C par by Gm. Alright? and the sampling time constant is basically whatever. R switch plus the output impedance of the sources times C bar. Okay? Understand? I mean, of course, if you look at it now, you can think of it also in the following way. What is this? It's a CMOS inverter, right? Or at least it looks like one. This is also a CMOS inverter. And not only that, the supplies of these two inverters, the supplies and the ground are, there's a way of disabling them by turning on those switches. So another way of looking at it is to, please note that the output of one inverter is connected to the input of the other and vice versa, and you have phi 1 which charges the two input voltages, and you have whatever the supplies of these guys connected by phi 2, and then you have phi 3 which resets the, okay. Alright, often this is also called a latch. So obviously, it turns out that unfortunately, while this all sounds okay, in practice there will be, all these transistors will not be identical. So there will be mismatch which will cause some error in the threshold that you use. So I'll cover that going forward. Okay, but this is the basic idea behind how you get a latch, and clearly there is not just one way of designing the voltage controlled current source. Okay, differential pair is just one of them, one way of doing it, right? You could come up with other, if you used any other voltage controlled current source, putting two of them like this would also give you similar behavior, right? So therefore there are any number of circuits for latches. Okay, in a lot of digital work, for example, the reset phase may not be there, right? Will not be there in fact, because the inputs are so large, right? And so on, right? But whereas we saw that if the reset phase phi 3 is not there, then when the input was large in one cycle and becomes small and negative, small and of the opposite polarity in the next phase, then you will almost always make an error, because the memory from the past has not been cleared adequately. So the voltage sampled on these two nodes is in error, which means that the whole thing is, you make a wrong decision on the. Does that make sense? Okay, so I'll stop here.